Good morning, everyone. It's good to be with you again today. We have mostly survived cylindrical and spherical coordinates. Um, uh, in time, after you start to work through that homework, I'm sure you'll have some questions, and I'm always happy to answer those before class, in office hours, or we can, of course, set up an appointment to work through more examples. I've been watching some of the dialogue that's been taking place in Slack, and I just really appreciated the back and forth and like watching people post their solutions and post their questions. You as a collective group are so much faster at responding to those questions than I ever could be. One Slack procedural question I have is, would it be beneficial to you if I started a new channel for you called something like homework questions, and maybe another one called assessment questions, to just help you to organize, figure out what's going on there? Would multiple more channels help you, or do you like it all being in one place?
That sounds fantastic.
Would
Yeah, I think that'd be good.
be good. Okay, so I will begin a couple more Slack channels for you today. They will be cleverly titled homework and assessment, and you could just post your questions accordingly. So I hope that helps a little bit. We have spent very little time talking about applications of multiple integrals. We have calculated areas and we've calculated volumes, which certainly are applications, but they're pretty simplistic ones. So in this coming section, we're going to talk about using double and triple integrals in order to calculate masses and centroids, the centroid being the center of mass. This particular section builds upon concepts that you probably explored back in Calculus 2, where you found x bar and y bar, and the moment about the x-axis and the moment about the y-axis. But that was a long, long time ago. And so this morning, before class, I recorded an 18-minute video kind of reviewing some of those things that you were supposed to have learned in Calculus 2. It's not the most exciting video. There's no snacks being eaten. There's no special effects, but it does walk through the work along, specifically the first 4 pages of the work along, kind of explaining what we would expect you to remember from Calculus 2. I say expect you to remember. The reality is probably, unless you've done this in physics or in engineering in some other class, you probably forgot all this stuff if you ever learned it in the first place. But it's not that difficult, and most of the stuff from Calculus 2 isn't helpful in the specifics, as in the formulas from before aren't going to be terribly helpful to you. It's just kind of the big gist that's important. And so I'd rather not spend our class time today talking about kind of those old formulas that are only marginally helpful to us today. So that's our new context. What I'd like to do is start by deriving the new double integral formula versions of these formulas and doing an example, or beginning an example. Okay, so just by way of context, this is section 16.6 on integrals for mass calculations. It's going to begin with some applications of double integrals. It should also be triple integrals. And in the video that I just spoke of, I did this entire review of section 8.3 from Jimmy Stewart Calculus. So it's the first 3 pages of the work along. So we're going to pick this up on page 4 of the work along, beginning by talking about density and mass in non-uniform objects. So to begin, let's consider an idealized flat object that is sufficiently thin that it can be viewed as two-dimensional. Such an object is called a lamina. A lamina is called homogeneous if its composition and structure are uniform throughout. So an example of a homogeneous or homogeneous lamina would be like a sheet of plywood. My favorite kinds of lamina that are not homogeneous are things like chocolate chip cookies or blueberry pancakes, where the chocolate chip, the density of the chocolate chip is different than the density of the bread part, or the density of the blueberry in the pancake is different than the density of the bread part. So those would be examples of non-homogeneous lamina, flat things, basically. So in calculus 2, we saw that the density of a homogeneous lamina is a constant and defined to be its mass per unit area. So just a comment here on density. Usually when we talk about density, we talk about it as the mass per volume. So it would be like kilograms per meter cubed. But in the context of lamina, we're talking about like a special kind of density that's specifically related to flat surfaces. So in this particular context, we don't have mass per unit volume. We have mass per unit area. Okay. Later on in the section, we're going to talk about triple integrals, and we will indeed have kind of the more traditional mass per unit volume. But in the world of lamina, it's just squared. Go ahead.
So the lamina density equation assumes that the density in the z direction is the same. It's constant.
Right. It's basic. Think it's a thin, flat sheet, so there is no z direction. Is probably the easiest way of thinking about it. Good. Cool. So this is when we're talking about a homogeneous lamina. Again, homogeneous would mean same density throughout. But what if we have a variable density? That is that the density can vary across the region, like the cookie, like the blueberry pancake, like most of the things that are out there, frankly. So to define a function for this variable density, consider the lamina to be on the xy plane and the point xy to be in the lamina. So maybe here's your shape. So this whole thing represents the lamina. Okay. And then we're going to focus in on an individual point, xy, and we could construct that small rectangle that you see there, centered at xy, and the mass of this particular rectangle is going to be that the delta m, the area is delta a, et cetera, and we end up with this idea that we could have density at a point. The key thing here is that we're going to have this row of xy will tell us the density at a point. Good. So don't overthink it. From this relationship, we obtain the approximation that the delta m, remember little m refers to the mass. So delta mass equals the density at the point, that's the row, times delta A, which is the area. Side note, what did rho represent yesterday?
Wasn't it like the radius for spherical coordinates?
Scaling factor?
Joseph's pretty close. It's not quite the radius, but it's similar to it. So it was the distance from the origin. Which is sort of like a radius, but not quite. So that was so yesterday, right? That's like yesterday's popular meme or whatever. Today, what does rho represent?
The density at a
Density.
given
Density.
time.
The density. It's the same letter, same Greek letter, same pronunciation, all that kind of stuff's the same. The context would tell you which is which. I don't know that I've ever had a student get confused about this later on, but at first glance, I could see how it could be a little bit confusing. So context will tell you whether we're talking about the spherical coordinate rho or we're talking about the density. Okay. So moving on. Here's the good news. So we get this relationship that delta M is equal to the density times the area. And so we could let the size of that area go to 0. We could let delta A go to 0. And you're going to end up with finding the exact mass. So it shouldn't come as a shock to you that the exact mass is going to be the double integral across that region D of rho xy dA. This will give you your exact mass. Does that derivation make some intuitive sense? Are there any questions before we do an example? Very good. Okay. I'm going to do this one by hand, but let me just walk through the basic process before we get going. So in our example, we have a triangular lamina with vertices at the given points. It has density function rho of xy equal to xy, and we're going to try to find its total mass. And our basic process is going to be very similar to what we've done previously. We're going to draw a picture, and then we're going to set up and evaluate the integral. Somewhere in here, we're going to set up some limits of integration. Let's see if we can work through this by hand. Okay. Ooh, you can see my right big note to myself. Very good. So we have vertices of our lamina at 0, 0, 1, 0, and 0, 1. And the given density function, we want to find the mass. So step 1 is going to be a picture. So my points are at 0, 0, 1, 0, 0, 1. And so we have some sort of a region that looks like this. What is the equation of this line?
X squared plus Y squared.
Not of the line, of the line.
X minus 1.
X minus 1?
Or 1 minus X.
1 minus X. Yeah. Okay. So step 2 is we can set up and evaluate. So we know that our mass is going to equal the double integral over the triangle. I'm just going to draw a little picture of a triangle here of what's our density function? I think you just said it, Damon, or someone said it.
XY.
XY, and then dA. We talked about this a little bit. What kind of integral is this? Like when I write it in this fashion, what kind of integral is it?
It's a double integral over a closed region.
So this is a double integral, exactly, over the closed region. And the catch with the double integral is we don't know how to evaluate it. We need to now write this double integral as which kind of an integral?
Iterated.
As an iterated integral. Good. You guys are on fire. Okay, so if we want to write this as an iterated integral, then we need to set up our limits of integration. So I'm going to draw my 3 arrows. I could draw them horizontally parallel to the x-axis or vertically parallel to the y-axis. I'm going to draw them vertically because I already have the equation solved for y. And so we notice that all of those are entering at y equals 0 and exiting at y equals 1 minus x. So our mass will equal the integral of xy, and our y values are going to go in at y equals 0, come out at y equals 1 minus x, and our leftmost arrow would be at x equals 0, and our rightmost arrow would be at x equals 1. So we've set up an iterated integral, and now we just have to evaluate. Antiderivative of xy with respect to y would be 1/2 x y squared from y equals 0 to y equals 1 minus x dx. At 0, this evaluates to 0, which is quite convenient to us. So we're left with integral from 0 to 1 of 1/2 x 1 minus x quantity squared dx x minus 2x squared plus x cubed dx. At this point, we're doing straightforward stuff. Which thankfully evaluates nicely to 1/2 times 1/2 minus 2/3 plus 1/4. Or looks like that's 1 over 24. Questions about the setup or the integration here? Okay. So in my experience, the actual integrations and the setup tend to be pretty straightforward here. The catch is that at least in the beginning, perhaps you don't remember how to set up or work with masses, and you might not remember the physics side of it. So what I'd like to do is put you into breakout groups and have you talk a little bit about mass And also it would help me if you could also talk about moments of inertia a little bit. And specifically, I'm guessing at least half of you have had some physics or have had some engineering classes. So if you've had physics or engineering, maybe you could lead out and just explain, just talk a little bit about what mass is, a little bit about what center of mass represents, a little bit about moments of inertia, and help catch up any of your classmates that have not spent as much time on physics as you have. Are there questions about moments or center of mass or mass itself that we want to talk about as a larger group? Very good. Very good. So we've previously calculated the mass of our lamina, and now we want to look toward finding the center of mass of our lamina. In order to do that, we need to be able to calculate moments. So the moment of a particle about an axis can be found as the product of its mass and its directed distance from the axis. To approximate the total moment of the lamina, we divide the lamina into small rectangles and add their moments together. So here, if we're looking for the moment about the x-axis, then we have some sort of a object, so to speak, or at some point, then we're looking for the tendency to rotate around that x-axis. And in order to know the tendency to rotate about the x-axis, we need to focus in on two things. One is the rho delta A represents the mass at the point. So this represents the mass. And oh, pardon me. Right. Back on track. So the mass of the object, and then it depends upon the distance that the object is from the axis. And so notice that the distance we are from the x-axis is given by the y value. So that's why the moment about the x-axis involves the y value. The moment about the y-axis will involve the x value. Again, the y represents the distance from the x-axis. The x represents the distance from the y-axis. As we let delta A get infinitesimally small, then this approaches a double integral, and we're left with our expected friendly formulas. So as the number of rectangles approaches infinity, we can find the total moment of the lamina. So the moment about the x-axis is moment about the x-axis, double integral, and again, there is a y value here representing the distance about the x-axis, distance from the x-axis, because we're talking about the tendency to rotate about the x-axis. Moment about the y-axis includes an x value here, because x gives me the distance from the y-axis, which dictates the tendency to rotate about that y-axis. So those are my moment formulas. I can put all this stuff together, and the lamina will balance at its center of mass, which has the formula of x bar equals my over m, y bar equals mx over m. And we call this point the centroid. I might have spelled centroid wrong. Having worked with this multiple times, the thing that's challenging about it is that is the fact that you have x and a y and an x all in the same formula. But note it's probably easiest to remember that if you have x bar, if you've got an x bar, then there's going to be an x in the form in your center of mass formula. If you have a y bar that you're looking for, or the average y value, then you're going to have a y in that formula. And the labeling of the moments is important for talking about it. So for example, if you're doing the honors project, you better be able to speak about it right. But in terms of actually just crunching through the questions, then what's important is simply remembering that y bar has a y, x bar has an x. Questions about those derivations and that rationale before we do an example? Very good. So what I'd like to do is find the centroid. That would be the center of mass of the same lamina that we worked with in the first question. Sorry, trying to change my windows. There. All right, so as you may recall, our shape was this triangular one, and we found the mass of our lamina was 1/24. And so now we want to find the centroid. And so our centroid is going to be x bar comma y bar. So we'll find x bar by finding the moment about the y-axis divided by the mass. And we already have determined that this mass is 1/24. And our y bar is going to be the moment about the x-axis divided by our mass. And we've already determined that that mass is, again, 1/24. So what we need to find here are the moments about the y-axis and the moment about the x-axis. To do this, we can go back to the iterated integral that we previously found. So maybe focus in on the my. So here is the iterated integral that we previously found. Now we're going to try to find my. And what I'm going to do to start with is I'm going to write the same iterated integral that we had before. So going from 0 to 1, integral from 0 to 1 minus x. And then I have x, y, dy, dx. And then because I'm looking for the moment about the y-axis, I need to include the distance that the mass is from, or any particle is from the y-axis, which would be an extra x. Something like that. And at this stage, the question just turns into a straight up integration question as before. So we have that this is going to be equal to the integral from 0 to 1, integral from 0 to 1 minus x of x squared y dy dx. One half the integral from 0 to 1 x squared y squared. Notice I pulled the half out front. From 0 to 1 minus x just a dx. X squared times 1 minus x quantity squared dx. Just ends up being a lot of writing. X squared minus 2x cubed plus x to the 4th dx. And all told, we have 1/2 times, this is going to work out to be a third, minus 2/3 plus a 5th. Oh, this isn't quite right. This is minus 2/4, right? X cubed over 3, evaluated at 1, minus 2x to the 4th over 4, evaluated at 1, x to the 5th over 5, evaluated at 1, which is some number. Which is equal to 2 over 5. So if we put all this stuff together, this tells us that the moment, this tells us that that x bar, which is equal to the moment about the y-axis divided by the mass, is equal to 2/5 over 1/24, which is a funny way of writing. I'm sorry, my arithmetic's bad. You guys catch it? This is 1 over 60. This is 1 over 60.
I got the same answer, 1 over 60, and I was like, what?
What? And the final result is 2/5. I got ahead of myself looking at my notes. Sorry about the confusion there. So you do your arithmetic right, you get 1 over 60. 1 over 60 divided by 1 over 24 would be 2 over 5. And this is the x coordinate of the centroid. So if we go back, you're like, well, what does that represent? If we go back to the picture, what that is saying is that the x balancing point is just a little bit left of center. It's somewhere on this line. X bar equals 2/5. In this particular instance, we have a whole bunch of symmetry. Our density function is symmetric, and so our y value is going to come out to be the same at 2/5. It will not always be this way, but we're saying that our balancing point is somewhere here at 2/5, 2/5. Are there questions about this? Very good. Very good. So you might ask, what's coming next? Rather than plowing forward and starting another example, let's just simply overview what's to follow. So what we've done is one super simple example of finding the centroid of a triangular shaped lamina with a non-uniform density. Non-uniform density is kind of the key. And so to do that, we had to find the mass, and we had to find the 2 moments of inertia. So we evaluated 3 double integrals to find 1 centroid. When we come back together again tomorrow, I will do a second example of finding the centroid of a flat lamina, and then we will expand this and say what would happen if instead of having a lamina we had a 3-dimensional solid. And so we will do an additional question finding the centroid of a 3-dimensional solid. note, in order to find, if there was no symmetry, in order to find the centroid of a three-dimensional solid, you would need to find the mass, which is the first triple integral, and then you'd need to find the moment about the xy plane, moment about the xz plane, moment about the yz plane, or three moments in order to find x bar, y bar, and z bar, or the centroid. So potentially you could be evaluating 4 triple integrals to find a single centroid. It's kind of a pain, maybe a little bit tedious, but it's not difficult. Just requires a little bit of practice. And the really good news is when as soon as you set up the first iterated integral for the mass, you can basically use those same limits of integration to evaluate all your subsequent multiple integrals. And as you've been discovering on your homework, the difficulty in evaluating double and triple integrals isn't really in the integration, it's in setting up those limits of integration. Are there any questions before we conclude? Very good. So, as we conclude the day, may your day be perfectly balanced with work and pleasure, family and friends, homework and fun work. May be perfectly balanced. May you find the centroid in your schedule. Thanks everyone today for being here today, and I look forward to seeing all of you tomorrow.